Hi there, in this video we're going to take another look at convolution, and we're going to prove that convolution in the time domain is equivalent to multiplication in the frequency domain, and also convolution in the frequency domain is equivalent to multiplication in the time domain. So this is one of the cornerstones of signals and systems, so it's quite important. So let's just get started. If we have some function x of t, when we find a Fourier transform we get some function x of j omega. Now if we take another function, say h of t, when we find a Fourier transform we get some other function h of j omega. Okay, now if we were to convolve this function in the time domain, so let's say we're going to generate another function y of t which equals x of t convolved with h of t. Now we've seen from the previous video that this convolution operator can be written as the integral from minus infinity to infinity of x of tau h of t minus tau by d tau. Okay, now what we want to do is we want to look at this here and we want to put it all into the frequency domain and see what happens. Okay, so what we can do is if we do the Fourier transform of y of t, you'll get y of j omega. Okay, now what we want to do is we want to do the Fourier transform of this here, which is a convolution. So we can write the Fourier transform out. That is the integral from minus infinity to infinity of, well, it's going to be some function, okay, times e to the minus j omega t by dt. Okay, now the function we want to do the transform of is the convolution operator, so that's this function here. So we'll just stick this in here. So we'll have the integral from minus infinity to infinity of x of tau h of t minus tau by d tau. Okay, now the rest of what follows is just a bit of jiggery pokery to try and bring this into the right format. Okay, so what we can do is we can change the order of integration, so we can take the dt in here and we can take the d tau out. Now we can do that because the limits of integration are the same for both. Okay, so if the limits of integration weren't the same we'd have to swap over the limits as well, but we don't need to do that. Okay, and also whenever we've taken this dt in, then this factor here tau, well, tau is not a function of t, so we'll be able to take the tau out. Okay, so we'll just go ahead and do that. That'll be our first part. So it's integral from minus infinity to infinity of, now I'll leave a wee space there, okay, and it's going to be the integral from minus infinity to infinity of, well, it's going to be h of t minus tau e to the minus j omega t. Okay, and we're bringing our dt in here, so a dt, and our d tau can go outside. Okay, so that's d tau, and our x of t comes out of this as well because t is not a function of tau, so we can just bring our x of tau out here. Okay, so that's us brought that out. Okay, now the next part, the final part, is a substitution. Okay, so what we want to do is we want to say, if we say p equals t minus tau, okay, then you can say that dt will equal our value dp. Okay, and you can also say our t is going to equal p plus tau. Okay, so you've seen this before, and it tends to crop up in a lot of these manipulations. Okay, so we're just substituting a value in. Okay, so let's substitute this in here. Okay, so you're going to end up with the integral from minus infinity to infinity of x of tau, okay, times, I'll keep the bracket round about it so you can keep it separate, okay, times, we're going to have our integral from minus infinity to infinity of, and it's going to be h of p, okay, because we've replaced the t minus tau with a p. It's going to be e to the minus j omega. Now the t gets replaced by p plus tau, okay, all by dp, okay, and that's all by d tau, okay. So now what we can do is we can separate these out, okay, because we can see that this e to the minus j omega tau, right, that's not a function of p, okay, so we can take this outside this integral sign, okay, so all will be left in this integral sign is e to the minus j omega p, okay, because that's obviously a function of p, okay. So whenever we take that out, we're going to end up with the integral from minus infinity to infinity of x of tau, and we'll take out our e to the minus j omega tau, okay, and we have our d tau here, okay, and that's times the integral from minus infinity to infinity of h of p e to the minus j omega p by dp, okay. So yeah, I think you can see now that if we write y of j omega equals, well, that's just the Fourier transform, okay, which is x j omega, and that's just the Fourier transform of h j omega, okay. So that there is shown now that when we convolve something in the time domain, it's equivalent to multiplying it in the frequency domain. Now, I've got an example of that in MATLAB. Now, what I'll do is I'll draw it out first, and then we can see it in MATLAB. Okay, so let's imagine you have some function here. It's a square wave. Okay, and let's say you're convolving that function with just the exact same function, another square wave. Now, when we convolve these two together in the time domain, so that's time and that's time, then what we're going to do, what we're going to get is a triangular wave, okay, like that. Okay, so that's the convolved function. Okay, so that's our x of t, if you want, we can write that. That's our x of t, we can say that's our h of t, and that's going to be our convolved function g of t. Now, when I take the Fourier transform of this square wave, now again we'll do this in MATLAB so you can see it, but we have already looked at it before, and it gives you the sinc function. Okay, function looks like that. Okay, so when I Fourier transform the other square wave, right, we're just going to get another sinc function, the exact same sinc function. Okay, I've got a carbon copy of above that looks like that. Okay, now it's our contention that whenever we convolve in the time domain, it's equivalent to multiplying in the frequency domain. Okay, so what we should get out here when we multiply in the frequency domain is this sinc function here. So that's sinc. That's sinc. What you're going to do is you're going to get sinc squared. Okay, sinc squared. Okay, so the sinc squared is just the all the terms are squared, so the stuff below the axis will be above the axis, okay, and everything's going to be squared as well. So you get something that will then run like that, okay. Right, so it's always going to be above. There's nothing below the axis, okay. So now, if in order for that to be true, we'd have to show that this triangle, whenever you do the Fourier transform of that triangle there, you should get this sinc function, sinc squared function. Okay, so now we'll just show that. Now we don't need to derive it analytically, so we could go through and do all the derivations, but I think we'll just go in and we'll show it in MATLAB. Okay, so we'll do the convolution first. Okay, I think I've got it set up here to go through a convolution. Go into MATLAB. Okay, so that's the two functions, right, that we're going to convolve. So that's our f of t and our h of t. So we're expecting to see a triangular wave whenever we go through this convolution. Okay, so let's just see here if I press return that there. So that should be okay. So that's it working through the convolution now. So you'll see when it comes in here, the overlap area is getting bigger and bigger and bigger. This signal is getting up and up and up in a linear fashion. Now it's crossover there, and now the area is getting smaller and smaller and smaller, so this height here is getting smaller and smaller, and when we come out here there's no overlap and we'll go back down to 0. Okay, so that's us done our triangular wave convolution. Okay, so let's just get rid of that there. Okay, and we'll bring back up our smooth draw. Okay, so you can see we've shown this here. When it gets convolved, gives us this here. Now what we want to do is we want to Fourier transform these here, each of them, and see if this this whole thing occurs. Okay, so the Fourier transform of our square wave. Now I've got these sitting again in a folder, so let me just bring up that folder, and let's say square wave Fourier transform. Okay, so let's have a look and see if you can see that there. So that there is the Fourier transform of a square wave, and it's not exact square wave I've shown, but it just shows you that that's that sinc function. Okay, so and it's actually in 3D. I think it is actually. I don't know if I can move that. You should be able to move this around. Okay, there you go. It's actually in 3D. Okay, so there's no any imaginary part. Okay, there's no imaginary part. Okay, it's purely a real function. Okay, because again, real even function of time gives a real even function in frequency. Okay, so that's the sinc wave. Okay, so what we're going to do is we're going to take two of those and multiply them together. Okay, so when we take the two multiplied together, we should get a sinc squared. Okay, now the sinc squared then should be equivalent, if I bring back up this. Okay, the sinc squared should be equivalent to taking the Fourier transform of the triangular wave. If it is, then we know that everything's okay. So we'll take the Fourier transform of the triangular wave. So again, I've got that up here. Triangular Fourier transform. There we go. Now fly MATLAB. Okay. So now, and there's the proof there. Okay. Computer's running a wee bit slow here. Let's see. Come on. Well, okay, the computer's running a wee bit slow here. I don't know what it's doing here. Transform. Oh, there we go. Let's see. There we go. So as you can see, that's the triangular wave here. Okay. And you can see that we've got the sinc function. Now everything's above the 0 line. Okay, so it's a wee bit spread out, but you can see that that is actually indeed forming that sinc squared function. Okay, so that's a sinc squared function. So that's really a kind of graphical proof from MATLAB that we do get whenever we convolve in the time domain, we get in the frequency domain, it's equivalent to a multiplication. Now, so just to finish, we can show that in the frequency domain, if we convolve two functions in the frequency domain, then it's equivalent to multiplying in the time domain. Okay, so what we're saying is if we have some function g of j omega equals that'll be 1 upon 2 pi times x of j omega convolved with h of j omega. Okay, now we just have the extra factor of 1 upon 2 pi because we're going to be doing the inverse transform. Okay, so that's equivalent in the time domain, okay, of saying g of t equals x of t times h of t. Okay, so that there is the equivalent of what we had done previously, but in the frequency domain. Now, the proof of that is exactly the same method as we use the proof of that. The only difference is you get an extra factor of 2 pi. So we still go through the process of changing the order and then substituting in a different variable for the values. Okay, but whenever you work through that same maths, you get this answer here. Okay, so we're able to prove that, and if we write the previous one down, if we say g of t equals x of t convolved with h of t, when we do the Fourier transform, it's equivalent to saying g of j omega equals x of j omega times h of j omega. Okay, so we can see that that's a kind of a transform pair. Okay, so that's all for this video, and I'll get you on the next video. Goodbye.